So in this question, we are given a person in a buggy is attached to a large parakeet by a rope, and we are given a diagram representing the tension in the rope and the buggy, and the angle is 55 degrees to the horizontal ground, and the mass of the person and the buggy is given to us as 150 kilograms. The velocity time graph is also given to us, and we are asked to calculate the horizontal distance traveled by the buggy from t equals 0 to 8 seconds. So for the horizontal distance, it's simply the area under the curve, okay? And so I will work out the area under the curve by splitting up the sections, the two sections. So first of all, I have this trapezium over here, okay? And then I have the rectangular section. So to work out the area of the trapezium, it is simply going to be, so I'll just label this as A and this is B. Okay, so for the area of A, under A, is simply the half times by A plus B, which are the two lengths. So this is 4 meters per second and the other one is 10 meters per second. So it'll be 4 plus 10 times by the height, which happens to be right in the middle, so 3 seconds, so times by 3, and that would end up giving me a 21 meter. And for the area of B, it is simply 10 times by the difference between 8 and 3, so that will be just 10 times by 5, which is 50 meters. So my answer is going to be 71 in total. So that's question 21, part A, done. At t equals 1 second, the buggy is accelerating. Use the graph to show that the acceleration of the person at t equals 1 second is 2 meters per second squared. So as we know, that acceleration is the gradient of a velocity time graph. So let's go back and look at where that 1 second is. So I'm just going to do it in a different color. So 1 is right here, so if I just go up and then across, that bit is basically right in the middle, which is going to be 6. So it's just going to be the difference, okay? Just make sure it's not starting obviously from 0, from rest. So it's going to be v minus u over delta t. V was 6, u was 4, and delta t is just for 1 second, so the answer is 2 meters per second squared. Okay, so for the second part, we are given that at t equals 1 second, the tension in the rope is 680 newtons, and the total horizontal resistance acting on the buggy and the person is R. Calculate the value of R by resolving the tension in the rope horizontally. So I would encourage everyone to, pause this video and try drawing a diagram, a free body diagram for this. And we're given that the magnitude of the tension is 680 newtons and the horizontal resistance is R. Okay, so if we just go back again to the diagram, we can see over here that the tension is acting 55 degrees to the horizontal. Okay, so if I just draw this out over here, let's say this is tension and the angle is 55 degrees. So this horizontal component is going to be, according to Sokotoa, is going to be t cos 55 degrees. Okay, and there is a resistance of R newtons acting in the opposite direction, obviously to the motion, and we have to be aware that the buggy and the person are accelerating towards this side with acceleration of 2 meters per second squared. Okay, so if we now resolve the forces horizontally, then we are going to have t cos 55 minus R equals ma, or mass times acceleration. We're given the mass as 150 kilograms, and so we can go ahead and put everything into the equation. I'm just going to keep this diagram over here. So t cos 55 degrees, R is this way, and acceleration is that way. So t cos 55 minus R equals m times a, and then therefore R is equal to t cos 55 minus ma. Okay, and t is 680 cos of 55 minus mass was 150 times by 2, and that would give me a value of, okay, 90 newtons, and that's that. So for the next question, number 22, we are given a pogo stick is a spring-based toy used by a circus clown for jumping vertically up and down. A compression spring is fixed to the bottom of the pogo stick, and the upper end of the spring is attached to a movable platform. And we are given some force constant, the mass of the clown, and that of the stick is negligible. So the overall mass is 68 kilograms, and we are given a few positions. So let's just understand what's going on over here. So I'm just going to zoom in. So we're given that in position A, the spring is fully compressed and the clown is stationary, and the height of the platform above the ground is 25 centimeters. And then in position B, the clown moves up to the original length, which is 45 centimeters. Okay, so it's moving up at maximum speed. Okay, that's fine. And then in position C, the clown is jumping above the ground. Okay, it's raised above the ground. So it is going to be, well, at a height of 76 centimeters given to us, and the clown is stationary. So let's check out what the questions are all about. In part A, we are to describe how the force constant can be calculated or can be verified in the laboratory. So for this one, we know that K is equal to force over extension. So if we can work out those two things, we can work out a graph of force versus extension, and then from there it would be a straight line and the gradient can be calculated. So if we could change the masses, okay, so various or varying slot masses in a mass spring system, okay, and then calculating, or rather recording, the corresponding extensions, for which then a graph can be drawn. Okay, graph of force versus extension can be drawn to obtain the gradient, which is the value of K. Righty, so for the next part, we are to describe the energy changes taking place between positions B and C. So clearly, the kinetic energy, which is the energy stored in position B, not just kinetic energy, technically it's also elastic potential energy, which gets converted into kinetic energy, and then gravitational potential energy as well. Okay, so because it's just talking about B to C, I would just stick to kinetic energy into gravitational potential energy store. Right, so for the next part, we have to calculate the maximum energy stored in the compressed spring. It is half kx squared in general, okay, the elastic potential energy stored, but in the compressed spring, it will be equal to half times k, which is 1.7 times 10 to the 4 Newton per meter, times by the extension. Now the extension is going from 0.25 to 0.45. So basically it is the difference between the two. Okay, so 0.45 minus 0.25 and squared. And once I put that in the calculator, I am going to end up getting 340 joules of energy. Okay, so let's move on to part D, where we are given that a student uses the following expression to determine the maximum speed, v of the clown, in position B. Maximum energy stored in the compressed spring is half, well, 68 is the mass, so they are basically using kinetic energy. So explain why this expression is incorrect, and you're not expected to do any calculations. Okie doke. So, well, first of all, they haven't thought about the gravitational potential energy. Okay, so the mistake that they've made is that they have not thought about the gravitational potential energy gained along with the kinetic energy. So that's what I'm going to write down. So GP, E, and kinetic energy are both to be involved in position B. Okay, so in position B. There we go. Right, so let's move on to our next question. Here we have two objects, A and B, which are traveling horizontally in opposite directions. The object collide in mid-air at a height of 120 meters above the horizontal ground, like so. And we are given the mass of A is 2 kilos and B is 3 kilos. After collision, the objects collide. Well, they are joined together. And the momentum P against time graph is given as here. So we have been given the graph for momentums before the collision, after, during the collision and after the collision. So let's have a look at the questions that they're asking us. So for the first part, we are to explain how the graphs demonstrate Newton's third law during the collision. So, well, we know Newton's third law suggests that if two objects are interacting, then their forces are equal and opposite. Okay, so if we look back at the graph again, if we could just calculate the gradient, okay, because the gradient here would represent the change in momenta, okay, of the two objects over the time taken, which is basically 1 millisecond, I should say. Okay, so for this one, if I just work out the gradient for A during the collision, it would be simply the change in y-axis, which is going from, this bit is going to be -4, and here we have just white as well. This is -6, okie doke. So for A, it would be -4 minus 20 over 1 millisecond, which is 10 to the power of -3, and that is -24,000 newtons. Okay, and for gradient of B during the collision again, it is going from -6 to -30 again over the same time period, and that gives me a value of 24,000 newtons. So what that means is the forces are equal and opposite. Okay, so the gradients represent the force, which are equal and opposite, and therefore it obeys Newton's third law. All right, so write that down neatly over here. So since force, which is equal to change in momentum over change in time, represents the gradients of A and B, right? They are basically opposite and equal and opposite. Okay, equal and opposite. I will include the calculations just in case, but you can always note them down. So I'll just say over here that force of A is that, and B is that. Cool. And since that's at a constant rate, okay, gradients are constant, and opposite as well. Therefore, the collisions are supported by Newton's third law. Right, so for the next part of the question, use a graph to show that the momentum is conserved in the collision. Okay, so according to the statement of conservation of momentum, we know that momentum before a collision is going to be equal to after the collision. So if we can prove that, we can prove this statement. So momentum of A is simply, 20, and of B is -30. Okay, so the overall momentum will be 10. So let's write that down. So momentum of A plus that of B is 20 minus 30, which is -10 kilograms meters per second. And afterwards as well, let's figure that out. So -4 and -6, which gives us -10. So there you go. They're equal, and hence the momentum is conserved. Next, we have to calculate the magnitude of the horizontal velocity of the combined objects immediately after the collision. So we know, it's asking just the magnitude, so we can ignore any signs over here. We know the momentum is 10 after the collision, so I'm just going to keep that in the bracket because it's not needed. And because the two objects are combined together, it is going to be 2 plus 3, 5 times the velocity, the combined velocity v, and therefore the value of the velocity is just 10 divided by 5, which is 2 meters per second. Right, so for the next part, we have been given that the air resistance has negligible effect on the motion of the object. Calculate the time taken for the combined objects to reach the ground after the collision. Okay, so for this we're going to use Suvat, so let's set that up. So we are to find out the time. We know that it's just dropping under it's a free fall, so 9.8 meters per second squared. We don't know much about the final velocity. Nothing's been given. Initial velocity is 0 because they start from rest, okay, originally, and the distance, the vertical distance that they cover is 120. Okay, so I'm taking this to be positive, the displacement is positive 120, and acceleration is positive 9.8 meters per second squared. So I can use S equals ut plus half a t squared to figure out what t is. So this is 120, this becomes 0 as u is 0, equals half, therefore times 9.8 t squared, and that's going to be 4.9 t squared, so 120 divided by 4.9, and then square root the answer. It will give me 4.95 seconds. Okie doke, let's move on. Okay, so for question number 24, which is all about waves, it says that stationary waves are formed on the surface of seawater in a harbour as incoming waves are reflected off the harbour wall. An observer is looking at these stationary waves state how the observer can tell that these are stationary waves. One of the most fundamental properties about stationary waves is that they form nodes and antinodes. So nodes are of no displacement and antinodes are of maximum displacement. So that's what I'm going to write down over here. So the observer can see that. Okay, so the stationary waves, or these waves, will form nodes and antinodes, or the appearance of nodes and antinodes will enable the observer to determine that these are stationary waves indeed. Now for part B, we are given that a wire is fixed between two supports like so, the wire is plugged in the middle and a stationary wave is formed, that of fundamental frequency. The tension in the stretched wire is given by the expression T equals 4f squared ml, where f is the frequency of the oscillating wire, m is the mass of the wire, and L is the length of the wire. A student is performing an experiment to determine the tension in the wire. He measures the following quantities like so, and for the first part we are to suggest how the student may have determined the fundamental frequency of the oscillating wire in a lab. So lots of different ways in which you can go about it. One of the ways I like is using a microphone connected to an oscilloscope, making sure that the wave represented on the oscilloscope will be that of fundamental frequency, and then I can measure the time period using the oscilloscope screen, and then from there I can work out the frequency, the fundamental frequency. And doing this in a quiet room and as dimly lit room will be ideal to avoid any background noise and light. Okay, so I'd say connect a microphone and to an oscilloscope, and then from there measure the time period, and then work out the frequency using 1 over the time period. And then I would say do this in as quiet room as possible. Just because it's 2 marks, I wouldn't worry so much about writing any more points. Right, so the first one is asking us to determine the wavelength of the progressive waves on the stretched wire. Alright, so let's figure that out. So we know over here that this is the length of the wire. Length of the wire is given to us as 0.62 meters, and from the diagram we can say that this length, okay, L, is representing half a wavelength. That means that wavelength is twice the length, okay, or 2 times 0.62 meters, and 1.24 meters is my answer. Then it's asking us to work out the speed of the progressive waves on the stretched wire. We know that F times lambda equals the speed. Okay, so 58 hertz times by the wavelength I just worked out, and that would give me 71.92, or, well, just 72 meters per second. Next, we have to calculate the absolute uncertainty in the tension T. Write down your answer to 2 significant figures. Okay, so absolute uncertainty. What is the formula of it? Well, it requires us to know percentage uncertainty, and we know that percentage uncertainty in the tension is equal to the absolute uncertainty over the actual value, okay, times by 100. So that's just a matter of rearranging this particular formula to work out the absolute uncertainty. However, we need to figure out what is that percentage uncertainty in tension first. So let's work that out, because we are given the values of percentage uncertainties in frequency, mass, and the length, okay, as 2.5, 1, and 0.5 respectively. However, because frequency is squared, I must double this value of 2.5. Okay, remember, when something is squared, the percentage uncertainty in that value is basically doubled. Likewise, if it is cubed, it will be 3 times as much. Okay, so it will be 2 times 2.5 plus 1% plus 0.5%, and that gives me a value of 6.5%. So now, therefore, the absolute uncertainty is going to be the percentage uncertainty, which is 6.5, okay, times by the actual value of the tension. Okay, now let's work that out as well, okay, using the values that we have. So tension, I'll just work that out just over here, that it will be 4 times 58 squared times 9.7 times 10 to the minus 4 times by 0.62, and that gives me a value of 8.09 newtons, and I'm gonna just pop that in here as part of my, so that just goes here, okay, and that will give me an answer of 0.53, that doesn't look like 53 newtons to 2 significant figures. Okay, so let's move on. Okay, for question number 25, well, potential difference and electromotive force can be defined in terms of transfer of energy per unit charge. State one other similarity between PD and EMF. Well, they have the same units of volts if they have the same formula. So, same units of volts. Okay, so let's see. Well, we have an electrical circuit. So in this circuit, we are given a resistance wire. The cell has an EMF of 1.5 volts and negligible internal resistance. And then we are given that AB is a resistance wire of length L, and the resistance of this wire is equal to the resistance of the fixed resistor. Okay, so S is a sliding contact that can be moved on the resistance wire. The distance between A and S is X. The potential difference across the fixed resistor is V, and the distance X is changed by moving the slider from A to B. And we need to draw a graph for the variation of, well, V versus X. Okay, so there's a lot going on here. First of all, the first statement says the resistance of this wire is equal to the resistance of the fixed resistor. Okay, so that means that the voltage across both components is going to be 1.5 volts at the beginning, okay, at start. So that's fine, we'll start with that. And then S is a sliding contact that moves from A to position B. Now, as it's moving, the length, okay, of the resistance wire is increasing. So the electrons will experience more resistance, and therefore the voltage will decrease. Voltage across the wire would go down. But as the resistance increases, the current also decreases. In basically other words, it's the current as well which affects the voltage, which is read by the voltmeter. Okay, because bear in mind that the resistance wire and the fixed resistor are connected in parallel, so the current is not the same. Okay, so if the current was constant, then the voltage and the resistance will be linearly relatable. However, current is not constant, current is decreasing. Okay, and so it would be a curve instead of a straight line, I'd say, and it would just go down like so. It would be a decrease until it reaches all the way to point B, where the voltage across the voltmeter will be 0. Okay, because the resistance is super high. Okay, so that's your graph for part I. Let's look into the next question. So now we are being given that the connecting wire BC is removed and the rest of the circuit remains unchanged. Explain the variation of V with distance x as S is moved from A to B. Ah, lovely. Okay, so kind of unfair for 2 marks, but oh well. Let's look back. So if BC is removed, the circuit might look different. In fact, it will definitely look different. It would actually, let's just write that down here. So if BC is removed, you're going to have still 1.5 volts. I'm going to have the resistance wire. Okay, and now since BC is removed, you're going to have the resistor. This is removed. You're going to have the fixed resistor in series actually. So this is your resistor R, and we know I've drawn the worst diagram ever. Okay, so we are sliding that contact from A to B. Okay, that contact should be touching the wire. So like so, let's just start with position X. Okay, that's X. Okay, and we have a voltmeter which is across the fixed resistor. Okay, so now that we have a series circuit, it would be a slightly different situation. The length of AB, okay, if you're moving from A to B, okay, the length is increasing. Okay, so the voltmeter reading would decrease. And therefore, because, well, that is the case because the total resistance will go up. If the resistance goes up, current goes down. And the voltmeter reading will also be going down. So AB and R are in series now. Okay, number 2, so as L increases, the voltmeter or voltage reading would decrease as the total resistance increases. Okay, so I hope that is understandable. Now for part C, we have a power supply of EMF 14.4 volts, negligible internal resistance, connected by 2 identical metal wires to 2 filament lamps. Okie doke. So we are given the current in the circuit, the potential difference across each bulb, and the total length of the metal wire as well, and as well as the area, cross-sectional area. So we need to work out the resistivity. Now, I think this is a fairly simple question compared to what we have just seen. Okay, resistance and resistivity are related to one another using this formula here. Okay, so we have the area, we have the length, we just need to work out the resistance of the wire. So the resistance of the wire is going to be, well, the total resistance, okay, which is 14, well, actually, I'm just going to write it down as V over I first, okay? So 14.4 volts is what's available, or is given by the source, okay? However, if the potential difference across each bulb is 6, that just means that you're only going to have 14.4 minus 12, okay? So just 2.4 volts available across the wire. Okay, passing through the wire. So 14.4 minus 12 over the current, which remains the same, which is 3. And that will give me a 2.4 over 3, which is 0.8 ohms of resistance. So now everything is really, really simple. I'm just gonna get this over here. So 0.8 times by the cross-sectional area is in millimeters squared, so be careful about changing the units appropriately. Okay, so 10 to the power of minus 3, so minus 6, okay, over 25 meters of the length, and that will give me a value of 1.73 times 10 to the power of minus 8 ohm meter. Right, so for the next question is asking us the number of electrons per unit volume, N, is 8.5 times 10 to the 28 meters per cube. Calculate the mean drift velocity V of the electrons in the metal. Okay, so this formula is given to us in the formula booklet, and it goes like this. Now we have pretty much everything here. Okay, current is 3, 8.5 times 10 to the 28 per meter cube, 1.6 times 10 to the minus 19 coulombs, and again the area to be in meters squared, which is that, and that's it. You just basically work it out using this, and it gives us the answer of 4.1 times 10 to the minus 4 meters per second. Okay, and let's move on to our, hopefully the last question. Okay, so question number 26, where we are dealing with work function of 4 metals being given to us, and it says electromagnetic radiation of wavelength 380 nanometers is incident on all the metals. Photoelectrons are just emitted from metal A. Okay. Explain in terms of the energy of the photons why metal C will not emit photoelectrons. Well, for it to emit photoelectrons, the energy of the photons must exceed the work function. Okay, so energy of the photons is given to us by hc over lambda. Okay, and if that is not exceeding the work function, which is that of metal C, okay, which is 3.3, then it wouldn't be, the photoelectrons will not be emitted by the metal C. And when you calculate this value of energy of the photons, okay, of the incident radiation with 380 nanometers, we end up, by plugging in everything in the right units, we end up getting 3.3 eV. Alright, and 3.3 eV is just equal to the work function. So that's the case. It's a very subtle difference. However, the energy of the photons, as I said, okay, must exceed the work function. So it's just equal to, it's not greater than. So that's why. So it must exceed the work function, but here it's just equal to it. Okay, so for the next part we have to calculate the maximum wavelength of the electromagnetic radiation in nanometers that will just eject photoelectrons from metal D. Okay, so the energy, as I said, hc over lambda, must exceed the work function. So that means that lambda can be rearranged to say that hc over phi, and once we pop in all the numbers in the right units, okay, so 6.63 times 10 to the minus 34, that's in joules a second, speed of light is in meters per second, and then we have the work function of D, which is 6.4. So 6.4 electron volts must be converted into joules by timesing it by 1.6 times 10 to the minus 19, okay, and once you pop in all these numbers in the calculator, you end up getting 194 nanometers. Right, so for the next part, we have been given that the metal B is now exposed to electromagnetic radiation of a different wavelength. The energy of each incident photon is 5.3 eV, and we need to calculate the minimum de Broglie's wavelength lambda of the emitted photoelectrons. Okay, quite a cheeky question here. So we know that first of all, lambda is equal to h over, well, the momentum. That's the equation which is given to us, okay? But what's not given to us is actually another form which I highly recommend learning, okay, is h over square root of 2a, well, EK, which is the kinetic energy, okay, maximum kinetic energy, times by the mass of the electrons. Now, this hasn't been given to you in the exam, and without this formula, I think this question might be slightly different or difficult. I haven't checked the mark scheme as to what they have suggested, but feel free to check it and see for yourself as to what else you can do. But over here, I'm just going to carry on because this comes naturally to me, where all I need to do is work out the kinetic energy of these photoelectrons and basically put that into this formula because I know the mass and I know the value of H. Okay, so how do I figure out the kinetic energy? Well, I know I have this formula, which thankfully is given to us, okay, is HF, which is the energy of the photons, equals the work function plus the EK max, okay, the maximum kinetic energy. So with this, I already know that that's 5.3 EV, okay, minus the work function of metal we're dealing with B, okay, which is 4.1. So I would end up getting a value of 1.2 EV, okay, for the kinetic energy. So now all I have to do is pop it in here, which is 6.63 times 10 to the minus 34 over square root of 2 times 1.2, again converted into joules, so like so, and the mass is 9.1, 1 times 10 to the minus 31, okay, kilograms. So after all this, we end up getting a very nice answer rather, and that is 1.12 times 10 to the minus 9 meters, or 1.12 nanometers. Okay, let's see what the next one has. Right, so we are given a diagram, we are given a lovely graph where it's asking us to, first of all, draw a line of best fit. Okay, so let's get this rolling. I'm going to get the ruler out and I'm going to go ahead and slide this through like so. Okay, that's done. Let's put this away. And now, what have you got? So this is part I done. Now for the next one, you have to use the gradient of this line and the Einstein's photoelectric equation to determine the work function of this material. Okay, so let's work out the gradient carefully, okay, because it's all in the units that we want, but just be careful that it's 10 to the minus 19 and 10 to the 14 here. Okay, so gradient is going to be the change in y-axis, so that is reaching a value of 2.25, 2.20, okay, and that's 0.5, lovely. So 2.20 minus 0.5 times 10 to the minus 19 here, divided by the change in x-axis, which happens to be 8 minus this bit right here maybe, and that is 5.25, so 5.5, okay, 5.5, well 5.2, okay, so that's going to be 8 minus, I'm just going to go for 5.25 to be on the safe side, and I'm sure there's going to be some leeway, so times by 10 to the power of 14 here. So that ends up giving me an answer of, okay, 6.18 times 10 to the minus 34 joules per second, which is actually joules, well, per second, kind of, you know, like, because it's per second in the denominator, so it becomes joules second. Okay, so that is a unit of H actually, and we can check that out using our equation because it's asking us to work out the work function, and we are going to need the value of H over here. So we know HF is equal to phi, which is a work function, plus maximum kinetic energy, and what we know is on the y-axis we have the kinetic energy max. I'm just going to write it down, EK max, okay, and on the x-axis we have the frequency. So if we rearrange this, we will end up getting KE max equals HF minus phi. Okay, now if we compare this with the equation of a straight line, which is basically y equals mk x plus c, we know that the y-intercept is the value of work function, okay? But we don't quite have that y-intercept and we can't do extrapolation, okay? So how do we work this out? Well, we can simply work this out using a bit of maths, to be honest. And what I'm going to do is simply work out the value of c, or the value of the y-intercept, by rearranging this equation. So let's write this down clearly. Right, so we know that c, or work function, is going to be equal to hf minus the kinetic energy, okay, maximum kinetic energy, 6.18 times 10 to the minus 34, okay, and times by the frequency, which is 5 times 10 to the 14, okay, and minus the kinetic energy, and be 0.5 times 10 to the power of minus 19, and that is going to give me my final answer. And my final answer is I'm just going to write that down over here, 2.6 times 10 to the minus 19 joules. Okay, and this brings us to the end of this paper. And so hopefully you found this useful. Let me know in the comments below if you have any questions, if you haven't understood anything in particular, especially for that electricity question. That was really good and kind of complicated. And so, yeah, let me know in the comments below how it went. If you have any questions, do let me know as well. And once again, thanks ever so much for watching.